they were first trying to develop rockets right after World War II, and you see them going up on the launch pad and then they just crumble. That was a buckling problem. The buckling phenomenon itself is when you're applying a compressive load to a structure and it can no longer withstand that load, and so it causes the can's cross-section to crush inward. So it's imperative that we understand the buckling process. That obviously was a very simple example, but what I have behind me here is a smaller laboratory scale test article that we would use to understand some of the basic physical principles of shell buckling and try and apply that to understanding larger structures. So what we have here is a small scale structure. We're studying various aspects of how it buckles, the effects of geometry and different types of load on the buckling behavior. You can see there's all sorts of instrumentation on here, so we're much more scientific than just crushing the can.
In a vice grip, right.
Yeah, right. So we then take that data and use that to compare to our models to see how well we really understand the process.
All right, in addition to the wires and the things I see attached, I see little tiny dots.
Yeah.
What are they there for?
Well, many years ago, NASA started working with some universities to develop what we call a video image correlation system. And what it is it's a series of digital cameras that we position around the circumference of the shell, and it monitors this speckle pattern that we've painted onto the shell. And during the test, as we're loading it, it's monitoring the movement of the shell wall.
The slightest movement will be picked up.
Sub-millimeter movements. And the really nice thing is, what you see here is a laboratory scale. We're down at Marshall also testing full launch vehicle size structures. We use the same technique, we just use bigger dots.
Mark, what's the difference between the testing, the shell buckling testing they did on Apollo, and the shell buckling testing you guys are doing right now?
Oh, that's a great question. And back in the Apollo era, they were just starting to understand sort of the fundamental physics of the buckling process. The best thing that they could do is run a lot of tests, but not really get a handle on the real physics. But they did a great job because they got to the moon.
Right.
What we're doing now, though, is we're applying more rigor to how we run our tests, the types of measurements that we take. We have new measurement technologies, we have new analysis tools that allow us to very accurately predict the behavior of these shells.
It's always increasing technology, huh?
Absolutely. It's hard to keep in front of it.
I know it is. You're doing a great job. Thanks so much.
Thanks.
Because composites are being used more and more in passenger vehicles like cars and planes, NASA researchers are taking a hard look at how they can make them more robust. Now, as they become more robust, they still have to maintain some of the benefits that composite materials have to offer, like weight reduction. Yeah, this is a tough task, but NASA researchers, well, they're up for the challenge. I caught up with NASA aerospace engineer Don Jegley to find out more about this new design called Perseus that may be a game changer in composites research. Don, how are you?
Hi, how are you?
Good to see you.
You too.
Good. So we're here today to talk about composites and Perseus, right?
Right.
Let's start from the top.
Okay, well, Perseus stands for Pultruded Rod Stitched Efficient Unitized Structure.
Okay.
What that means is we have a large panel, and this is a Perseus panel.
Right.
And if you look real close in here, you can see stitches. It's all held together by stitches. And what you'll notice when you look at this panel, rather than a normal aircraft panel, is you don't see any fasteners. In a normal airplane, you've got rivets all over the place holding every part together. In this case, we have no rivets.
Right.
Everything's held together by stitches.
Okay.
Now, composite materials have been around for a long time. NASA have been working with them for 40 years. Industry's working with them, and they're now getting out into real aircraft structures.
Gotcha.
But what's different about Perseus is a couple things. First of all is the stitching. Composite materials, composite structures are put together using layers of graphite epoxy or carbon epoxy materials that's all built up into whatever configuration you're looking for. With Perseus, what we're trying to do is build very large unitized structures. So we can get away from all those fasteners by putting in the stitches and by making very large parts. So composites are useful. Composites are good because they're lighter weight than aluminum. With lightweight structure, you can cut down on your fuel costs. And of course, one of the things NASA is looking at today is reducing the amount of fuel that's used and producing less pollution. So we're looking at the next fleet of aircraft would be lighter and more fuel efficient.
What are you doing with this piece?
Okay, this panel was fabricated by Boeing. We're going to do the testing here, and what we're going to do with it is we're going to put it in this test machine, so we're going to slide it back.
Right.
We're going to take the platen here, raise it up, put the panel underneath it, and then position the platen so that it's just at the top of the panel.
Okay.
Now, this machine can apply up to 1 million pounds of loading. So what we're going to do is bring the platen down to the surface of the panel and then slowly apply load to push the panel down.
Okay.
While we do that, we're going to monitor the behavior of all the strain gauges here to look at what the panel's feeling, and we're going to have additional measurements. So we're going to look at the displacements, how the panel moves in a couple different directions during the test. So what we're going to try to find out is how the panel behaves while we're pushing down on it, and then we're going to take it to failure. And what's going to happen is we're going to get a failure somewhere in the panel, probably somewhere in this region here.
Okay.
And what's going to happen is we'll see what the failure load is and where it starts, and then we'll take a look at all the instrumentation we have and compare that to our analysis. Because right now we have an analysis of the panel, but the reason that we have to do the testing is we have to make sure our analysis is right. And because composites are a lot newer than aluminum, and particularly Perseus doesn't have that much of a database to draw from, we have to do a lot of testing to make sure we really understand the behavior. You wouldn't want to put this kind of structure on a real airplane unless you can predict its behavior. And that's what NASA's been trying to do with Boeing, is develop the technology to really understand that behavior so we can predict it.
Well, good luck on the test.
Thank you very
and
much.
Definitely, and we hope to see this on a future airplane.
So do I.
Right on. Okay, so far we have seen some of the ways that NASA uses composite materials, but NASA's not the only organization to be using them. Nah, there are many industries that use them too, like the auto industry. Whether it's a huge car company or a startup, all of them are looking for ways to combine strength with weight reduction to make their cars more efficient. One company called Edison 2 is taking that weight reduction to the limit. They have developed a car for the very light car category of the 100 miles per gallon X-Prize competition that they feel is the most efficient auto platform ever built. This little car is amazing. It takes design cues from some of the top race cars in the world, while also being incredibly safe with phenomenal mileage. I spoke with my buddy Oliver Kutner to find out more about it. So this is the VLC?
Yep, the very light car.
Very light car. Tell us all about it.
Well, we were trying to build the most efficient car. It's designed to be a 2 or 4 seat car, and it gets 111 miles per gallon combined EPA, 129 on the highway, and we did it by basically building the lightest possible car with the lowest aerodynamic drag. The car substitutes pressure drag for friction drag, like an airplane or a rocket would. You know, these race cars are carbon fiber, and you know, this was a race for a lot of money, so we didn't leave any stones unturned. What it really is, it's kind of like space exploration. What we tried to do is to depart from the ordinary and build it very light. And the auto industry has a very difficult time doing it because of all the legacies, the large corporations and the huge amounts of money involved in making a major shift. And this car demonstrates that the shift exists.
Can you tell us some about the materials that you use to build this car?
It's steel, aluminum, and carbon fiber, and just using it wisely where necessary. It's a steel chassis car, but it's a carbon fiber bodied car, and the wheel centers are carbon in this case.
Do you have any examples or something that you show us?
Here's an example. The wheel is unsprung weight and it's rotating mass. So we actually have the center of the wheel out of carbon.
Okay.
And the outer part is a cast magnesium piece and the inner part is a machined aluminum piece.
Huh.
Altogether, I think this is a 6 pound or 7 pound wheel. And you know, it's an example of using more difficult and more costly materials where their payback is greatest. And in this case, it was worth it, we felt, so that's why we did it. A car is a series of compromises, and you know, you have to also balance cost in all of this. So while we all want a super hot rod that's all carbon fiber, which might be the best solution, it may not be the most realistic if you want to sell 1 million copies. So you put your trump card material where it makes the biggest difference.
So Oliver, tell us how you got the idea for this car.
It was the X Prize. I mean, the X Prize said, you know, you can win $10 million if you build the most efficient car. And then I went to my good friend Ron Mattis, who's a long-time American Le Mans Series and Le Mans race car designer engineer. And he basically reeled me down to reality. There's no substitute for efficiency in the platform, and that's what this is.
Can you tell us how it works?
Well, in this case, we have a gasoline-powered engine. It runs on E85, and but this car can be run on any fuel source. It could be a diesel car, it could be a gasoline-only car, it could be a hybrid, an electric. The efficiency comes out of the design of the car itself. That's what does it.
Is it powerful?
It's quite powerful. It doesn't have that much horsepower, but it's quite quick and it handles extremely well. The NASA programs have been really crucial to a lot of material science and how we do things, and in certain industries they've changed the way things are done. But in automobiles we've kind of missed the mark, and in many ways we're still building the same 4,000-pound car to move the 200-pound person. If we embrace this as a method of how to build cars, regardless if they're electric, hybrid, diesel, gasoline, the United States of America could become an oil exporting nation. Just embracing the principle of this, the efficiency would be a leap from what is today.
Oliver, thank you so much. You know, I look forward to driving one of these VLCs.
Thank you.
Maybe a basic black?
Next time you come, we'll have one for you.
Please, make sure it's all glossed up for me. Hey, good luck with everything.
Good.
Take care. Thanks, man.
As you can see, composites have really changed our world.
That's right. And with NASA on the case, composites will continue to improve for years to come. And that's all for now. I'm Johnny Alonso.
And I'm Jennifer Pulley. We'll catch you next time on NASA 360.
They still have to maintain some of the composite materials.
To even next. I knew I was one of these days I'll let them.
Okay, so far we have seen some of the ways that NASA uses composite materials. Do you have something that you can show me that, you know, shows that it's not as
Now, this switch to composites is because weight distribution. No, I'm just making up words now.
Composites will continue to something, one more time. Give me one more time, I'm sorry. I'm not in my mind frame right now.
Want to get to know Charlie Bolden? NASA Edge heads to Washington to get an in-depth look at the NASA administrator's life and legacy. Plus, a bold look at how NASA plans to move forward here on Earth and in space. Charlie Bolden is ready. Who will get there first?
It is great to be back in the nation's capital.
Beautiful day out.
Yeah, nice sights to see.
Hey, make sure you stay focused today.
Oh yeah,
Okay.
of course. It's the standard. We got a lot of.
We've got quite a bit of work to do today, so
Oh yeah, I got it under wraps. Don't worry.
no sightseeing.
Now, why do you want to be a spoil sport?
That's after we get the work done. So.
Oh no, hang on. You got to stop. I got to get out.
Right here? Oh, okay.
I got some things I got to take care of. I'll catch up with you guys later.
Can you open the door for us?
Yeah,
Go ahead.
safety first.
Yeah. Think I'll make it past the gate?
Nah, I doubt if he'll get past security.
Yeah.
I'll play my cards right. I'll beat them to the punch.
Whoa.
I'm sorry. I'm here from NASA Edge. We have an interview with Charlie Bolden, and I really need to get in there quick so I get that interview.
Your name, sir?
Blair.
You need to come with me.
Ow, that's quite a grip you got there. Is that legal?
Yes, sir. Headquarters is Patrol 1-1. Charlie Bolden is ready for his interview with Chris.
So, Charlie, I have a few dates from your past that I'd like to kind of see if you reflect upon.
Okay.
The first date I have is January 12th, 1986.
I tell people a lot, it was a highlight in my life. Not quite like the birth of my son and daughter day.
Right.
Or my marriage day. But a very important day in my life because it was the beginning of a period that was absolutely incredibly high. It was STS-61C. Very exciting day. We had already been to the pad 4 times prior to that, 4 scrubs, and then finally we went out beautiful morning, just before dawn, and lifted off, and it flew off into the sunrise.
Now, you've been a military pilot before that point, flying A6s?
I flew A6s in Vietnam and then went to test pilot school and flew A6s, A7s.
So what was your experience like getting ready to go, launching on shuttle, having experience flying around, pulling high G turns in a military aircraft, and here for the first time you're going into space? I mean, what was that feeling like compared to...
I think the apprehension was probably as high as it was, say, going on a combat mission in Vietnam, although you relaxed very quickly. When the solids ignite and you lift off, all the apprehension is gone. The vehicle is vibrating all over the place, which was somewhat surprising because the simulators we use are very, very good. They don't adequately simulate the vibration.
There you saw the solid rocket booster separation. I had planned to do a lot of reach and visibility checks, and in feeling the force on my chest, I just said, well, forget about that. I'm going to sit here and enjoy the ride.
The G level is very low. It's about a G and a half at liftoff, so nothing anywhere close to what you experience in a tactical jet, for example. But then, right after liftoff, you sink into your, okay, this isn't a simulation, but it sure seems like it, and you go right into doing what you've been trained to do.
Is he okay in there?
He's okay.
No. If he gives you any problems, let me know.
Okay, thank you, I will.
Now let's move a little bit forward in time. This is 1994. February 11th, 1994.
February 11th, 1994 was a date that I knew was coming, and in a way I dreaded it, because at the time, long before I flew, I had advised my crew that this would be my last flight. My wife, my family, and I had talked it over in the course of the training for STS-60, and we had decided that they had decided that I'd had enough fun, and that I should grow up and go off and do something productive.
Right.
And we made the decision after